I thought because we have enough papers here, I'll be exempt from giving a talk. But, you know, Italy, there are bosses here. And, you know, the boss said that I have to give a talk. And if the boss says, you know, you have to do it. So anyway, all the good stuff was taken. And so I'm stuck with what an old, not very popular president in the US used to call the vision thing. So I have to give you the vision thing. So, so you know, we are in an era of short attention span, and so to keep the attention of the public, we have to invent new buzzwords every few years. And so if you ever notice, machine learning is passé. Now we are in the era of data science. And so I was sitting with the provost. So all universities in the States, and I think also here, think they have to do something. They have to have present in data science, otherwise the students are not educated in the right things. They wouldn't get the job at the famous Google. So I was sitting with the provost, and you know, so there were me as computer science, there were a statistician, and she looked at us and she said, data science, what's actually the difference between statistics and machine learning and data mining? And okay, so there were statisticians there were computer scientists. And so now if you are, and of course, her question is, you have to understand, her question is kind of, I already pay for this expensive computer scientist. I'm already paying for statistician. Now they want something else. Why do we need it? Okay, so what do you answer when you sit on this university's committee so you can be the right, politically correct, nice, corporate person? And you say, well, no, there's actually no difference. You know, we're all, you know, looking at science, and we're not, you know, taking data and try to get something out of the data. And then, of course, there are some of us who, you know, not collaborate in the all nice, no conflict Swedish idea. And so, of course, there is difference. And there's a lot of overlap between, and you know, the way to really think about it is not the particular term, but there is the computer science approach, and there's the statistics approach. And there's a lot of overlap, of course. We're all using similar tools, but there's different emphasis, okay? And if you talk with statistician, at least if you talk with honest statistician, there are some. And then a statistician really cares about the accuracy, the confidence level of the result. A true statistician is happy to tell you that there is no conclusion in the data. It's better to say no conclusion than, you know, if you don't have statistical significant conclusion, you are very happy to say there's nothing to say, no significant observation. Computer science is slightly different in that sense. Well, okay, of course, we emphasize computation, and that's very important because when you talk with statisticians, they very easily throw this Bayesian model that require you to integrate on 15, you know, variables, nested integral. They'll show you how you do it. Okay, so definitely we care about computation. That's very important. But I think no one will be too offended here if we say that computer scientists also turn into the, what I would call the expediency. We want results. Correct, not correct, you know, we know it's correct. We need to show something. There should be a graph at the end of the paper, okay? And so we are happy to show the best available conclusion, even if it doesn't come with, you know, very strong, you know, statistical guarantees, or even if either we don't know or we can prove it, we don't know how to analyze it. Okay, now there's no question that our side is the successful side, and so the computer science is the approach, is the great success in data analysis. So the obvious question, you know, if it's not the statistician that is the computer science that really makes the difference now in data analysis, does it mean that accuracy is overrated? Is it really not that important to give, statistically significant results? Okay, well, obviously it's not the case. And the reason is that the great success so far in big data, or in data analysis, was in big data. Okay, so where are the big successes? Without getting to particular application, the big successes are when we have a lot of training data. It's not enough to have data. You have annotated data. You need to have training data. You have a lot of training data, which means that you can actually do real cross-validation, not folding, leave one out, real clean cross-validation, or when you work with sequential data, you do A/B testing. That's the corporate way they call it. Okay. But that's only one of the questions. The other characteristics of the big successes are areas in which speed and frequency, to some extent, compensate for accuracy. Okay? And of course, one of the big successes is algorithmic trading. And why algorithmic trading is so successful? Well, okay, you need to start with some knowledge, okay? But we all know, even if you're not very familiar with all the details of martingale theory and stuff, intuitively you know that if you do a lot of gambles, and if your risk on each gamble is relatively bounded, okay, and if your gambles are even slightly biased toward you, you do it enough times, you win your big money, okay? So, in order to do algorithmic trading, in order to figure out, what ad to put on a particular page, in order to do all of these things, yes, you need knowledge, but the knowledge doesn't have to be perfect. You just have to be a little bit better than random, and you do it enough times, you have enough opportunities, you succeed. Okay, that's great. The problem is now that everyone wants to do the same thing. If Google and, whereas to Sigma can make tons of money from big data, also my small company should be able to make big money out of data. And now it becomes tricky, okay? So, here is something from the Wall Street Journal this weekend. Okay, so we're also going to do medical diagnostics using data analysis. Okay? Well, is it still the case that speed and frequency compensate for accuracy? Well, if it's your diagnostic, then you probably don't think so. Maybe the government who pays for that still thinks so, but if it's you, you would like to have some better guarantees. Okay? And here's another example. So this was from the New York, so that I'm not politically biased for the previous talk. Here is for the Wall Street Journal. Now we're in the New York Times, so we are covered. And I like the end of this statement. But the means and method of validating the reliability of self-driving cars have not even been invented yet. So here you got to have cars driving around you and around your children on the street. And it's not only that we haven't guaranteed that they'll, be perfect, we don't even know how to do it. Now, of course, the answer is that also the people who drive around your kids are not perfect. So and maybe it's enough that they'll be a little bit better than that, but it would be nice to be able to analyze that. Okay. So where all this is taking us, so what I'm really trying to claim is as we take this great success of big data from the obvious places of success, and we try to project it to all other areas of our life. For example, maybe we follow John and we'll have algorithmic judges. There'll be less bias, but we still would like to know, somehow guarantees on what they're doing. So as we move to using data science in more and more application, it's very important to have, and I want to emphasize practical, so now this is not a theory talk, this is about practical, computational efficient method to quantify the quality of the output, okay? And you don't want to hear it from me, so here is a big name, Michael Jordan. So again, for the Americans here, a few years ago, we were all had to, well, at least those of us who beg NSF for money, we had to talk about computational thinking. That was the buzzword at that time. So now Michael Jordan came with a related buzzword, which is inferential thinking. And buzzword or not buzzword, what he says is the right thing. You know, it's not enough to run statistics. It's not enough to run some machine learning algorithm. We actually want to know how correct it is, or in the terms of statisticians, is where are the error bars and the confidence interval. Okay. So it's a little bit misleading to say that the computer science, machine learning, or data mining doesn't have theory. There is actually an extensive, very rich theoretical analysis of generalization error, tools for analyzing it. And the only problem is there are two different cultures that are completely divorced from each other. There are the practical data analysis people and the beautiful theory that seems to be much too complicated to be used. Okay? So what what I and people working with me, and in particular Matteo's PhD, Matteo is sitting somewhere here, really look at a question which is not your typical theory question of how to prove something very complicated, but actually how to take this very complicated, seemingly impractical theory and try to get something that actually works in practice. And so the question is, can we obtain practical sample size and error bounds, and error bounds and sample size are going together with each other, building on the rich theory. And that's from another president. Yes, we can. That was the slogan of Obama. So what I'll show you here is, in the very short time that I have here, I'll show you a few techniques and some examples, but mainly a lot of open problems. And I'll say one thing about the previous talk. So the question at the end of the previous talk was, can we add another feature and another feature? And it was really along what I'm trying to argue here, when the answer was, yeah, we can add more features, but the computational is going to be harder. No one asked the question, as we add more and more features, do we have enough data now to validate that? And your data somehow has to grow with the number of features. So when we talk about sample sizes, error bounds, they're going together. As your problem will formulate in a second, as your problem becomes richer, you'll need more data. And it's very important that you have a hold on some kind of bounds on how much data you need. It's not enough that your convex optimization would come up with the result of the computation. Who knows if this result has any meaning with respect to the data that you have? Okay, so that's the kind of question we want to answer. Okay, so we'll do some theory now, and then we'll see if it's relevant. So asking whether machine learning algorithms are correct or not has a long history, long before there was machine learning, and that was the main tool come from Vapnik, and Vapnik and Chernovsky's, but it's basically Vapkin. And Vapnik noticed the following thing, but if I have time at the end of the talk, I'll show you that this is actually not exactly necessary. But he said the following. So assume that I want to learn a set of functions. Okay, let me actually go directly to the next slide. Okay, so assume that I have a set of hypotheses that I want to decide which of them is the right hypothesis. Okay, so for each hypothesis, I can define the loss function of that hypothesis with respect to the data. What's a loss function? Is some kind of measuring how bad is the hypothesis with respect to the data. It can be 0, 1, and if it's classification, but often we work with continuous functions, it's easier to work with, okay? And then it says, well, okay, so we have all these functions which are the loss functions. Now, as we get more and more data, so these are our samples, as we get more and more data, of course, the average of our loss function would converge to the expectation of the loss function. Okay, so that we know, or under any mild condition happens. The real difference is now we want this we want the soup over all the functions to converge. Okay, so we know that each function converges to its expectation. The average of a function converges to expectation. What we want is that the soup over all the functions converges to the expectation. Why do I want that? Because if I want to decide which of the hypotheses is the right one, I need to figure out the error, the loss with respect to each of the hypotheses, and then I'll find the best one. Okay, so in order to figure out which is the best one, it seems like I need to estimate the loss for all the hypotheses. And I have to use one set of data to do it simultaneously for all the functions. So that's where the difference between the standard statistics. We want to compute with one set of data, estimate for a large class, it might be even a finite class, an infinite class of function, and we want all this estimate to converge uniformly. Okay, so that's the uniform convergence, basic, and that's the base for all, analysis of generalization error, most of them. Okay. And then came pack learning, and pack learning basically said, well, let's put all this in terms of computer science, so it's not enough that we have all the samples, it's not enough that the set of functions would satisfy the statistical condition, we want also to be able to do it in polynomial time. Okay, so that's the okay, and then it took a few years until pack learning people realized that to some extent Vapnik already answered the major question. And the problem is that in order to answer the pack learning question of what is learnable, not necessarily efficient, what you need is what's called the epsilon net theorem. And that's slightly unfortunate because the really interesting theorem is the epsilon sample theorem. But somehow the motivation of the pack learning took the computer science slightly in the wrong, slightly deviation from the really interesting thing. So what the epsilon theorem says, it says the following. Assume that you have a set of elements and a set of sets of elements, of the elements. Okay, think about this once you have a distribution over it. Think about it as the sample space and a collection of events. Okay, and the collection of events can be infinite. Okay, and now you want a sample, which is going to be finite, such that for any event in R, the probability of that event is well approximated by what part of the sample hit that set R. Okay? So, in other words, I want a finite sample that simultaneously estimate all the events in capital R. Okay? Now, of course, that's too much to expect. There's going to be epsilon error, and that means that I only estimate the events that are not too small. Okay? And the big thing is that I can do this if and only if the VC dimension of this, it's called a range space, if the VC dimension of this is finite, and if it's finite, I actually know how many samples I need. Okay? So the big thing that you do in data mining, and also in machine learning, which is I have to estimate uniformly, simultaneously, a lot of events. Well, the fact that I can do it or not, or the question whether I can do it or not, really depends on having a finite VC dimension. And if I have a finite VC dimension, I actually know how many samples there are. Great theory. Talk with your machine learning friend in the department, and he'll tell you VC dimension, yeah, great theory. I don't have time to teach it in the course because no one really uses it. Okay, that's not what we teach in real machine learning courses. Okay, so so we ask, well, can you actually use it? Do you actually get practical bounds if you use VC dimension? Okay, so there are two problems here. First of all, it's hard to compute the VC dimension, okay? And the other one is that the VC dimension is a kind of a worst case analysis. And I'll get to this point in a second. But it ends up that even with all these problems, you can still get very good results for some problems, okay? So I won't get to all the details. That's part of the work of Matteo. And So here's one of the problems that is really classic for data mining, and it's kind of a prototype of prototype problem for deciding, for checking also the thing is the frequent item set. So basically you get transaction. Think about each line here is, you know, a transaction in a supermarket, what a person bought in a supermarket, and you want to know an item set is a subset of a transaction. So, and you have the alphabet of all possible element, all possible product you can buy, and then you look at subset of this, and you ask which subset is frequent. Okay, what do you buy often together? And you know, we think about it as a supermarket, it come up in tons of other applications. Okay, so assume that you know there's a distribution of this transaction. How many transactions I actually need to see in order to get a very good estimate of the frequent item set? Okay? Well, again, there can be exponential sets, exponential number of possible item sets, and I need to estimate all of them within a good bound in order to figure out which one is the best one. Okay? So how many I need to do? Okay, so if I do just the regular union bound, then you know the number, this is the number of transactions, this is the frequency of A, item set A in transaction, then this number is a binomial distribution. You can use Chernoff bound, and then you know you work the detail, and you say that you see that your sample size, in order to get an epsilon approximation, your sample size has to be a function of all the possible elements that you might buy. So think about, you know, Amazon, you know, this is all the possible elements that Amazon sells, and that's going to be, your sample size is going to be linear in that. Okay, that's not very practical. Okay, now you say, well, okay, but that's really taking it to the limit because I know that, you know, people don't buy everything in Amazon. They buy only a few of them. So let's assume that I have a bound on the maximum transaction size. Again, you work out the details, and your sample size is going to be a function of the length of the maximum transaction and the log of the number of elements that you can buy. Okay? Well, okay, so I now is replaced by log I, but we're still a function of I. Okay? So now what happens if I use it as I look at it from a VC dimension point of view? So let's, what I'm doing time. Okay. We'll not go through the details, but the funny thing is you can actually define a very easy bound on the VC dimension. And the VC dimension, so if there's something like we call the D index, which is like the age index that worries all of you. So the D index of D is the maximum number integer such that the data set contain D different transactions with at least D items. Okay, so it's almost like age index. So for example, here the D index will be 3 because there are 3 transactions with at least 3, but it's not 4. Okay, and we can show that the VC dimension is bounded by that. Okay, how good is it? Well, obviously, if you have all the transactions are the same size, then you don't gain anything. But for example, if your transaction have power law distribution, then you're going to gain, this is the longest transaction, and the VC dimension is going to be, you know, only sublinear in that. Okay, that theory, you run it, what's happened? You run it in practice on some benchmark data set, and you get that you really, you know, perform much better than if you use union bound. Now remember, we wanted simplicity. The idea here is not to prove another fancy theorem, but to show that we can do something simple and get results. Okay. So, but VC dimension is really not the way to go, because VC dimension is kind of a worst case way of measuring the complexity of a set of hypotheses. So a lot of work now is focusing on something called the Rademacher averages. And what happened here is that unlike the VC dimension, you incorporate the input distribution in the bound. So in VC dimension, it might be that there is some complexity somewhere in the sample space, but you actually never been there. You never go there. There's zero probability of being there, but it still affects your VC dimension. So now, if you do Rademacher averages, then it takes the distribution into account. You can show, well, it applies to general function, not to 0, 1 functions. You can show that it always lower bound the VC dimension, so it's always better. And you can also compute it from a sample, which is another very good tool. You can also do it for the VC dimension, but the cost is higher. Okay, won't get too much detail. What is this Rademacher averages? Well, assume that S1 and S2 are large enough samples that they have already the uniform convergence property. That means that they estimate every function in F more or less correctly. So that means that the expectation over one sample has to be very close to the expectation over the other sample, which is very close to the real expectation. Or in other words, the soup of the difference is very small. So what the Rademacher complexity does, it says, well, okay, why taking two samples? Let's take one sample and partition them randomly into what looks like two samples. So the way we do it is we use these Rademacher variables, which are variables that are with probability half-half, either -1 and 1, +1. And then we look at the expectation over all the partition of this sum, where some of the observations are in plus and some of the observations are in minus. So it's kind of a little bit more sophisticated way of writing this one. And if this is very small, then I know that, well, no. So, okay, so just a second. So this is the definition of the Rademacher. And the only thing I want you to know is that, let's skip that. So the Rademacher average really captures what we want. That means that if I look at the maximum error in estimating any of the function in a set, it's indeed bounded by twice the Rademacher complexity. So if I can compute the Rademacher complexity, in particular, when I say compute it, the idea here is compute it as a function of the sample size. I want to know what sample size bring the Rademacher complexity to be small enough so that my generalization error will be small. Okay, and again, well, you can get higher bound on this. I don't want to get to this. I just want to say that another work of Matteo showed that you can use this, the Rademacher averages for the same problem, frequent item set, and the whole thing, computing it is now a little bit more complicated. Again, bounding the Rademacher average is a little bit more complicated, but he got a very good result. And here are application. Here is what you get from the Rademacher complexity compared to the VC dimension. So you get much better. You can get the same result with a much smaller sample. So what I want to show you, what I want to tell you out of all these two examples is that, surprise, surprise, what is considered highly esoteric theory, if you really try, you can apply it and get actually practical results. And the difference is that it's not only that the algorithm works as fast or even faster than previous algorithm, but now they come with certificate. They come with statistical guarantees on the quality of the output. Okay. But these are easy examples. And in particular, what I show you is an example for supervised learning, which is relatively the simpler case. What we really want to do is, next is to go to sequential learning. And that seems much more complicated. And in particular, it's not clear how to work with temporal dependencies. Even the theory doesn't have very strong, result about how to compensate for dependencies. I mean, there are some cheap results where you block it and you assume that the dependency mix or disappear very fast. But if you want more than that, then it's very hard. Okay. Much time? No time. Okay, so let me just finish with one hard, really hard question. So, so this is going back now to the beginning, to Vapnik from the 70s. And Vapnik said, well, in order to learn, you need to have a uniform convergence over all the loss functions. But that's actually too much to require, or might be too much. because I really don't need uniform convergence. I don't need a very good estimate on the loss function of all the possible hypotheses. I need a good estimate of the loss function that are close to the optimal one. For those that are very far, I can afford to have a much weaker estimate. So if a loss function is extremely bad, even a relatively weak estimate would already tell me that it's bad. So in fact, I don't really need an epsilon delta approximation for all, uniformly for all the loss function. I only need it for some of them, the reasonable one, okay? And this is the base, the very intuitive base of the what's called local Rademacher averages, which you're trying to compute in significant slices of the sample space. And this is an area in which there is a beautiful, very hard theory, but we really don't know how to apply it to practice. So I think that's one of the ways to continue. Okay, thank you. Yeah.
So I was just curious, in the original proof of the epsilon sample theorem, the proof proceeds by doing a random splitting of a finite set, which is like your formulation of Rademacher average. So does that suggest there's some connection even in the original proof?
Yeah, so all these tricks are somewhat similar, but actually the interesting thing is that proving the Rademacher result, but the Rademacher result is, well, the first result is the average. The fact that the Rademacher complexity bound the average. This is actually very easy to prove. You just say, well, okay, let's take two samples and look at the difference between them, and then there's some hocus pocus that get the minus and plus in the right places. So this is much easier to teach than teaching the epsilon delta result, the epsilon